Hello everyone, I'm Kaize from Beihang University. It's really my pleasure to have this chance sharing my paper and my recent research. My title is A Piezoelectric Force Sensing Graph for Acupuncture Quantification. So let's begin. Here is the contents of my presentation. First, I will briefly introduce the background of acupuncture and my motivation for doing the project. Then, sensor fabrication and system construction is included. After developing a simple technique for calculating the features, I will evaluate the performance and discuss the results. Let's get into the first part. As we all know, acupuncture enjoys a good reputation in China for a long time, and it is now globally utilized for various kinds of treatment. Due to its effectiveness and rapidity of adverse effects, the curing process of nearly 800 units proves to be effective, including respiratory system diseases and various nervous system diseases, such as epilepsy. But traditionally, there is no quantification means for storing master skills or examining Chinese learning effects. Due to the opaque manipulation of needle, it is hard to circulate the technique on a large scale, hence strongly limiting the development of acupuncture. Instead, quantitative research allows Chinese to master acupuncture skills quickly and provides a means for establishing quantification standards. Therefore, modern facilities should be enticed for quantitative research. Let's see some related work in the last few decades. Those work could be collected as advanced information technology and manipulation parameter measuring system. However, they suffer from limitations to some extent. Advanced IT, including video action capture, advanced robotic system, and ultrasonic simulations, all focus on recording the manipulating rate rather than stress measurement, and its cost is very high. As for the parameters measuring system, ATPI acupuncture detector can merely detect stress in single orientation, which is not enough for quantitative research. So, it is necessary to design a new stress measuring system which can not only detect normal and shear stress, but also facilitate the uses. In order to design the measuring system, we should first select the suitable material. Here comes PVDF. It's called polyvinylidene fluoride. You can see that it has many strands which exactly meet our requirement. We are able to pick a small volume to stick in glove, and it is able to detect both normal and shear stress by using different piezoelectric coefficients. Most importantly, it presents an advanced dynamic interaction and high accuracy on stress detecting. What's more, its high tensile resistance enables a longer working lifetime. Yet it is very important in the research. And as you can see here, these are the orientations of normal and shear stress. So after selecting the suitable material, let's get into the next part, sensor fabrication and system construction. As you can see in the figure, these are sensors and the graph. You can see that it mainly consists of 5 layers, with PVDF thin film in the middle. Plastic substrates serve as a cover and protection, and beneath the plastic layer are the Cooper electrodes. This picture explains how the sensor works. When you touch the film, the charges will redistribute, which is called direct piezoelectric effect. Through direct piezoelectric effect, charges induced by stress could be transmitted to the readout circuit through Cooper wires stuck in growth. Here, both D33 and D31 are piezoelectric coefficients. This is D33 and this is D31. Sensor with higher D33 is sensitive to normal stress, while the other with higher D31 is sensitive to shear stress. So we can use thumb to detect normal stress and index finger to detect shear stress. Insular tape here is used to fix Cooper wires and prevents electromagnetic interference from the environment and the human body. This is the schematic of fake-out circuit. The PVDF sensors could be regarded as a current source with capacitance Cp and resistance Rp. The cable part is the parameters of the wire, which is negligible in this situation. Charge amplifier is the main part of the whole circuit, followed by a voltage follower. The parameters here, VCC is 5 volts, feedback capacitance Cf is 100 nanofarad, and RF is 30 million ohmega. This is the structure of the whole system. The Cooper wires are stuck in the internal layer of the growth, and as I just mentioned, the charges can be transmitted through Cooper wires to readout circuit. After being amplified, the fault signal can be uploaded to computer through analog digital converter in Arduino Uno. Then, relevant parameters like pitch stress, twisting speed, dispersion, and average period can be extracted through computer. Let's get into the next part, development of features calculating technique. This is the flowchart of data process. We use digital filter to prevent EMI and other noise from affecting the results. Stress parameters and manipulating parameters are extracted through computer, and ultimately we can get normal and shear stress parameters and twisting, lifting, thrusting parameters, which is of significance to acupuncture quantitative research. Specifically, parameters extraction include 3 steps. According to the general features of voltage time graph, we set the threshold of 2.55 volts or 5 volts for normal stress and 2.53 volts for shear stress, identifying and labeling the valid data. Since the force voltage responsivity has been experimentally obtained as 0.3 voltage per Newton, the computers will automatically record the relevant information, like lasting time, number of fork sensing, etc. After that, we can program in personal computer to calculate the relevant parameters. And this is just a brief introduction. Next part is performance evaluation and results discussion. After fabricating the system as is shown in the figure 5, Dr. wore the glove and performed the complete manipulating process of acupuncture. Usually, a complete manipulating process includes insert phase, twisting phase, and listing thrusting phase. Figure 6 is part of the results. The figure depicts a detailed, normalized stress time graph. You can see that distinct phases are clearly classified and presented. Here, insert phase refers to the process of the needle penetrating the skin. Twisting phase and lifting thrusting phase are 2 of 4 fundamental manipulating ways in traditional Chinese acupuncture. Based on this figure, we could use the technique mentioned above to calculate the parameters and further study the result. After extracting the parameters from the process, we can get stress parameters as well as manipulating parameters. Table 1 is the summary of the major parameters of normal and shear stress in acupuncture. It is noticed that the number of force sensing of two different orientations is not equal, referring the distinct pattern of the force. Though the tallest peak of normal stress is slightly lower than shear stress, it has a larger average stress. In addition, shear stress lasts longer in every period and turns out to be more steady due to the lower dispersion. Now let's see the next table. After briefly analyzing the results of stress parameters, we should come to the manipulating parameters. Table 2 is the summary of major parameters of twisting and lifting thrusting phases in acupuncture. The results show an obvious difference between two phases, since two manipulating way of acupuncture is very different. On the whole, two phases have nearly the same average period and the dispersion. The twisting phase has a higher average stress and longer phase lasting time. What's more, its high velocity is higher too. This is some other parameters like speed and dispersion of the two phases. This is the velocity graph and this is the dispersion graph. As you can see in the previous normalized stress time graph, twisting phase is slightly faster than lifting thrusting phase. Dispersion, in this case, reflects the steadiness of stress. Twisting phase is unsteady generally since most of the time it is above the zero. On the other hand, lifting thrusting phase remains stable but changes sharply in a short time since the result here is relatively high. And this is all the parameters we can check and the quantitative research we have conducted. So let's have a conclusion. Experimental results prove that the device is effective in detecting both normal and shear stress. Through fork signals uploaded to the computer, relevant parameters like speed and peak, which are significant to quantify the process, are successfully extracted. The piezoelectric graph based system developed in this work not only allows Chinese to quickly master the acupuncture skills, but also provides a means for establishing quantification standards, hence enhancing the development of acupuncture. However, the presented system is just a small step for acupuncture quantitative research. We still get plentiful work to improve the system and conduct more experiments. To improve the accuracy on stress measurement and detect parameters like the depth of needle penetrating, we could add inertial sensors like gyroscopes and accelerators. Designing a hardware arithmetic circuit is a necessity, since it can largely shorten the processing time, which is very important to doctors. Furthermore, as is shown in the results, each phase has its unique characteristics. By applying machine learning to the research, computers are able to identify and classify different phases automatically, which does help to doctors on their further study. And that's all of our work. Thanks for your listening.